All right, let's get started. Hello and welcome everyone to Ontario Farmland Trust November Winter Webinar. We're so happy to have you all here today to explore some best management practices to improve soil health. My name is Teresa. I'm the Communications and Community Engagement Coordinator at OFT, and also here from OFT to support us with any tech issues is Rachel, our Resource Development Manager. Before we begin, I do want to start with a land acknowledgement. OFT works all across Ontario, but we are centered in Guelph on treaty lands and traditional territory of the Mississaugas of the Credit of the Anishinaabe peoples, the original and ongoing protectors of these lands. Guelph resides on Treaty 3 between the Lakes Purchase Territory, representing an agreement and respectful partnership between peoples of different nations. As settler nations work to reconcile our relationships with Indigenous nations, we want our work at the Farmland Trust to reflect the respect deserved to the legacy of the original caretakers, whose stewardship of the land has allowed us to enjoy the land's beauty and bounty today. Especially given that the role of land dispossession has been used as a tool of colonization, this context is really important for us to acknowledge. Now for some webinar housekeeping. So throughout the webinar, we encourage everyone to share your comments in the chat, share your thoughts in the chat. Feel free to introduce yourself, where you're coming in from, and maybe where you work, and if that's relevant to you. However, if you have any questions for our speaker, Owen, you can submit those questions using the Q&A feature. If you have a similar question that has already been submitted, you can also upvote that question by clicking the thumbs up icon, and this will just move the question up in the queue, allowing us to answer the most popular questions first. As I mentioned, Rachel is here to provide support during the webinar, so if you have any technical issues, you can message her directly using the chat feature. And for those of you who might be unfamiliar with OFT, allow me to introduce us. We are a not-for-profit registered charity and the only provincial-wide conservation organization with a mission dedicated to protecting and preserving Ontario's agricultural landscapes. It is so critical that these lands are protected because Ontario's prime agricultural land is a finite, non-renewable resource that comprises less than 5% of Ontario's land base. Farmland is the foundation of the agri-food sector that provides us with locally produced foods, employs more than 800,000 Ontarians, and contributes over $49 billion annually to the province's GDP. And yet we're losing farmland at a drastic rate. Ontario has lost 20% of our farmland in the last 40 years. The rate of farmland loss nearly doubled between 2016 and 2021 to a rate of 9 family farms or 319 acres lost a day. And once farmland is developed, it's gone forever. So it's more important now than ever before that we protect our food-producing landscapes for future generations, for environmental resilience, and for strong local food systems and economies. So what exactly do we do at OFT to accomplish this mission? We do have a few program areas. Our core work is permanently protecting farmland. And we do that by partnering with landowners who want to make sure their land will always stay in farming, whether that's through a farmland easement agreement or by donating their property to OFT. The first farmland donation that we received was in 2024, which is our Bourgeois farm in Tiverton. And with this property, we're able to launch really exciting programs like our Farmland Access Program. We're developing a demonstration farm for best management practices and establishing a community food and farming hub for knowledge sharing, educational, and conservation initiatives and events. We also engage in provincial policy discussions on changing land use policy that impacts farmland, and our education and community engagement programming includes several outreach initiatives that aim to educate the public on what threatens these lands and how we can collectively work to protect them, including webinars like this one. So to date, we have permanently protected 28 properties amounting to over 2,900 acres of farmland, forest, and wetlands across the province. So on this map, you'll see the areas in which we have protected farms, which is the tractors. And then we have our current projects also on that map, which is the blue and white circles. So I'd like to mention also that it is with the support of our dedicated donors and supporters that we're able to make such an impact on farmland preservation. And with that, we will begin the webinar today. This webinar is supported by the Greenbelt Foundation as part of our future vision for the Duffins Rouge Agriculture Preserve project based in Durham region. So if you'd like to learn more about that project, you can visit the link that Rachel will be dropping in the chat right now. So we are so happy to have Owen Ricker here today, sharing his expertise on best management practices for soil health, including techniques such as drone-seeded cover crops, cover crop grazing, and nitrogen inhibitors. Owen is the Ontario Soil and Crop Improvement Association's Farmer Engagement and Research Liaison for the Living Labs project. He comes from a cash crop and chicken farm in Haldimand County. After graduating from the Agricultural Science program at the University of Guelph, he worked at Woodrow Farms and pursued his Certified Crop Advisor designation. Owen, thank you so much for joining us today. I'll pass it over to you now.
Thank you. And thank you so much for having me. It's a real honor, a real privilege to be here with you today to talk a little bit about what we do. So now, just like we rehearsed, I'm going to try to share my screen here. And we practiced this a couple times already. And hopefully we have success right now. Is that sharing properly?
Yes.
Thank goodness. Okay, fantastic. Before I get started, I apologize. I realize now that I'm on camera, I am having a bit of a poor hair day. A few of these hairs sticking up and outwards, so hopefully that doesn't offend anybody. I promise I did not just roll out of bed 5 minutes ago. I have been up and at 'em this morning. And I'm excited to talk to you today about some of the research that we're conducting through the Living Lab Ontario project that the Ontario Soil and Crop Improvement Association is responsible for delivering here in this province. And so I work for the OSCIA. I'm the Farmer Engagement and Research Liaison for the Living Lab Ontario project. And so I'm excited to come and share some of that information with you today. So let's just jump right into it. Here we go. So first and foremost, for anyone who doesn't know, what is a living lab? Simply put, it's a farm innovation project that is supported by research. And right now, our project objectives are to mitigate climate change through reducing greenhouse gas emissions and trying to increase carbon sequestration on farms in Ontario. Um, how do we do that? Well, these are the three core principles that all living labs share, regardless of the current goals. So first and foremost, it's user-centered innovation. And so our end users are farmers. So we ensure that the farmers are included in the research from the very beginning and the planning stage, all the way through the implementation, and then through the results, collect the data collection, results analysis, and then planning again for the next year. And that way we ensure that the data and the results and the outcomes of the innovation and the research we're doing is applicable to farmers in Ontario. Next, we work in partnership. And so we partner with researchers from the University of Guelph, UBC, the Ontario Ministry of Agriculture or OMAFA, Agriculture, Agri-Food Canada. So all of these folks who are experts in their fields, and we bring them together with the farmers who are experts in their fields, if you will, and we create these projects, on-farm research and innovation projects through these partnerships. And finally, it's real-life context. So like I said, all of this happens, all of this research and innovation happens on real working Ontario farms so that the outcomes of these projects are feasible and applicable for real farmers in Ontario. And so we have a whole host of research activities that are spread all the way across the province. So each of those dots on the map on the right side of the screen represent one of our farms, farm cooperators who has a living lab site on their farm. And then on the left is a list of some of the research activities that we have going on at those farms. And so today we'll take a closer look at the nitrogen inhibitor trials, the cover crop grazing, and the drone seeded cover crop trials. We don't have time to go through them all, but we also have other initiatives like the manure storage emissions management project, which is focused on reducing the methane gas emitted from liquid manure storages on both dairy farms and hog farms. We've planted some pollinator habitats around the province. We provide farmers with profit maps and survey them on how they can use those maps in order to use their inputs as efficiently as possible. And then we have projects that look at different field management practices that can increase the amount of carbon sequestered in field crops and on permanent pasture land. We have another site where we monitor the water quality of the water that's leaving agricultural fields, whether it's through surface runoff or tile drainage, and then what practices impact the amount of sediment and the amount of other material in that water that's leaving the the farmland. But for today, we'll stick to three so that we can get into a little bit more of the details with three of these projects. And so we'll kick things off with the drone seeded cover crop project. So in this research activity, we're partnered with the Ministry of Agriculture, Ontario Ministry of Agriculture, and Jake Monroe specifically is a researcher on this project. And I should say before I speak to any of these different research activities, I myself am not a researcher. I have the privilege of sharing this research with you today, but let's make sure that credit is given where credit is due because it's not myself that is setting this up. I'm a liaison. I try to help connect the farmers and the researchers and make sure we get all the data collected in any given season. But that's what I'd like to say. I'm sharing other folks' research that they've conducted and worked hard on. And so what are we doing with this drone seeded cover crop trial? Well, everyone knows that after wheat is harvested in Ontario, there's a fairly large window of opportunity to plant a cover crop if that's something you'd want to do on your farm throughout the month of August or even into September. And you can drill it in or use a broadcast spinner spreader or whatever your preferred method is. And you have a little window there at the end of summer and early fall to get that done. But after corn and soybeans, that window is a lot shorter, particularly for corn, of course, with the later harvest date. By the time you've got all of your corn done and you're ready to, maybe if you wanted to try and get your drill out, maybe there's already snow on the ground. Sometimes we don't finish corn well into the new year and it's January, February, there'd be no point in trying to plant into those conditions. And so what our question is, what if we are to use a drone technology to seed cover crop into standing corn and soybeans at the end of summer or at the very beginning of fall, so that once we harvest those crops at the end of the season, they're already there in the ground, they've already germinated, and they can use the rest of the season sunlight to put on a little bit more growth before the winter. Um, so we're testing two different things. First, how does the drone seeded cover crop compare to a cover crop that's planted using a drill or using a broadcast spreader after harvest? And so we have treatments side by side that were seeded with a drone, seeded with a drill, seeded with a broadcast spinner spreader. And then we also look at how do different species of cover crops compare between or compare when they're all seeded with the drone. So side by side treatments of cereal rye, of oats, and of red clover that were all seeded with a drone. And so this is the first trial that I'll go through on this activity. It took place in Elgin County. It was seeded in the fall of 2024. So just over a year ago now, on September 26th, we went in there with a drone and seeded 90 pounds to the acre of cereal rye into the standing corn. And on the photo of the right, that's taken 3 weeks after that seeding happened. And you can see there's a smattering of cereal rye plants that have hit the ground, got enough moisture to germinate and sprout, and we have a little start on a crop there. And then after the crop was harvested, the farmer went in and planted on November 8th. Again, it was 90 pounds to the acre of cereal rye. And then a couple days after that, he used a broadcast spinner spreader to seed cereal rye, again, 90 pounds to the acre. And then the farmer went out on the very last day of the year. This is taken December 31st of 2024. And on the left side of the screen is a photo of what that drone seeded treatment looked like. So you can see a fair amount of growth on that cereal rye, especially between the rows of where the corn was standing. And then in the center, you can see the drilled treatment. If you look really closely, you can make out the 7.5-inch rows, but the plants are a little bit smaller in that case. And then on the far right is what was broadcast spread with a spinner spreader, again, after harvest, a couple days after the drilled treatment was put in. So a less dense stand, but still a little bit of cereal rye poking through there amongst the corn stubble. So then in the spring, cereal rye is a biannual cover crop. So that means after winter, it's going to come back just the way winter wheat would. And so this image was taken by a drone on May 5th. It's an NDVI layer, which is it's a vegetation index. Basically, anything that shows up as green here on this image is a green, growing, healthy, photosynthesizing plant that's covering the ground. And anything that shows up as brown is either a dead plant, dead residue, bare soil, a lot of bare soil, or a really unhealthy plant that's not photosynthesizing and doesn't have very much chlorophyll in its leaves. And so what we see here, it's a little convoluted if you try to make out every single one of these treatment strips. So just focus on the top 5 with me for a moment. And I'm actually going to laser pointer my cursor here. So now I hope you can all see that. The northernmost treatment strip was seeded with the drone. And you can see 2/3 of the way down this plot, we have fairly reasonable stand and emergence and ground cover as of May 5th. And that's the cereal rye that was seeded and growing well in that area. Now, on the very west side of this plot, we were advised by the farmer there is a sandy knoll that runs along this field over here, and that may have attributed to the less dense stand over at this end of the field. Lack of moisture, reduced germination, fewer plants there to start taking off and growing in the spring when it got some sunlight. However, nevertheless, here we have about 36% ground cover. 36% of the ground is covered with a green growing plant. Right below that is a control treatment. Now we would expect to see basically no ground cover in this case, but we still see 13%, and we're suspicious that it looks as though it was some bleed over from the drone seeded treatment. Maybe the wind was blowing a little bit that day, or the treatment didn't perfectly line up over top of where it's supposed to be. And you can see on the north edge of this control treatment, there's some plenty of green growing plants there that is likely due to some bleed from the drone treatment that's directly above it. Below that was drilled in. And so here we see just a very even, consistent stand of cover crop here of the cereal rye, 66% ground cover. It was a very nice fall last fall. So even though not seeded until November 8th, we had lots of sun and moisture and heat throughout the rest of November and even into December last year. And this crop survived the winter just fine in this treatment. Below that is another control, and this is more like what you'd expect to see. 1.2% ground cover. It's not directly adjacent to a drone-seeded treatment in this case, and so that's what we'd see here. Okay, and then below that is a broadcast spinner spread, and most of this cereal rye, it looks like it's right behind where the tractor would have driven. This was supposed to be a 50-foot wide spread pattern, but the spinner spreader struggled to throw that light cereal rye seed right to the margins of that treatment strip, which is likely what we're seeing there with most of that greenery right in the center of that treatment strip. But we still have something there, green and growing, which was exciting to see. So we went out on May 5th, and then we went out again on May 30th this spring to take biomass samples from each of these different treatments. So we have the broadcast treatment on the left, the drilled, and then the droned on the right. And the little green bar was the sample results, the amount of biomass as of May 5th this spring. And so the same time that that NDVI image was taken in the slide previous. So the least amount of biomass in the broadcast, that's not surprising after looking at the image above. And then the drilled and the drone treatment had very comparable amount of biomass between them at the May 5th sampling date. But have a look at what happened over the next 25 days. By the time we got back there on May 30th, of course, we've seen lots more growth on all of them, but it's this separation that's interesting from the drilled and droned on May 5th, very comparable amount of biomass in all of those treatments. And now the drone, maybe doesn't double, but significantly more biomass come May 30th. And the reason for that was obvious. I was actually out at this site with Jake on this day, on both days, and we could tell why that happened. It's those earlier seeded rye plants, they were just more mature. They had actually bolted, they had headed out and put on plenty of tillers. So even though there were fewer individual plants that had germinated and started growing in the fall and were there again in the spring, there was more biomass total because each one of those plants was further along in its maturity cycle. And so a lot of tillering, more biomass by the time we got there on May 30th. And that was the same time that the farmer desiccated that field with a passive Roundup in that last week of May 2025. And so that's what we were looking at this past spring. And so here's just a little image for you. On the left-hand side, we have the drilled treatment. This photo was taken on May 5th, right between the drilled and the drone treatments that were right beside each other. So this was before like that bolting and the heading out and all of the tillering had happened that I just talked about that we saw on May 30th. But even on May 5th, you can see on the left side those really clear, even rows of drilled cereal rye, strong there as of May 5th this spring. And on the right-hand side, some taller, mature plants that were droned on, and a real concentration of them between the rows of where the corn was standing last fall, which makes sense. If you're broadcasting cereal rye seed onto a standing cornfield, the cereal rye that's going to make its way down to the soil and get enough seed to soil contact to germinate and take off is going to be the seed that falls right between the rows of corn. And so we see very little rye right on top of the row, but a nice stand of rye between each of those old rows. So on May 5th, we also grabbed some some soil samples to test the nitrogen, nitrate, and ammonium levels in the soil. And so on the far left of the screen is the control treatment. This is not a surprising result. In blue, we have the nitrates, and in green, we have the ammonium. So the ammonium is fairly comparable across the board, but the nitrates, not surprisingly, much higher level of nitrate in the soil in the control treatment that had no cereal rye growing in it. And then anywhere that there was cereal rye growing, whether it was the drone seeded, the drilled, or the broadcast treatments, we had less, fairly comparable amount between them, but less than the control in terms of nitrogen that was available for the plant. Not surprising, there's green growing plants in the ground in the springtime that's taking up that nitrate as it becomes available for the soil for the plant. It's taking that nitrogen up out of the ground and using it to grow, whereas the control would not have had that going on. And so it's just something to be aware of. In this case, we were planting soybeans throughout the season of 2025, so the farmer's not concerned about it. with soybeans fixing their own nitrogen for the most part. But it's something to be aware of if you're planning to put corn into the field after having a cover crop, especially a cover crop like cereal rye that's known for being a nitrogen scavenger. You're going to have less nitrogen available in your soil in the early season. You're going to want to plan for that and fertilize your crop accordingly. So, yeah, not a surprising result, but an important one to keep in mind. Okay, and as promised, I mentioned it wasn't just cereal rye that we seeded. We also tested what would happen if we seeded cereal rye through the drone, oats through the drone, and red clover through the drone. And so this was again, it was done on the same day, September 26th of 2024, just over a year ago. We seeded 50 pounds to the acre of oats at three different sites, one in Hamilton, one in Norfolk, one in Oxford. So we had 50 pounds to the acre seeded. And then when we came back and took biomass samples, at the most successful, the highest biomass site in Hamilton, we had an average of 200 pounds to the acre of biomass. And in this photo, that's what 200 pounds to the acre looks like. And so I would consider it limited success. We might still get some of those advantages of having the cover crop planted, like maybe some reduced erosion and maybe some excess nutrients being taken up out of the soil and some roots building up some soil structure. But really, when we seed 50 pounds to the acre, we'd hope for a greater return than 200 pounds to the acre of biomass on the surface. So what we've done this fall in 2025 to address this limited success that we saw in 2024, we've gone ahead and done two seeding dates in 2025. So we did one in the last week of August, so 3 weeks earlier than what we did last year, being the 26th of September. And then we did a second seeding date within the first 2 weeks of September. And so earlier seeding date, hoping to get those plants to put on a little more growth before the frost will kill the oats, generally speaking. And so that's what we've adjusted for next year for this trial. And I've actually left out a slide here. The next one, you're not missing out on much. It was to describe what happened with the red clover. And basically, the answer was nothing. It was just an image of basically an empty field. So we seeded 10 or 12 pounds to the acre of cereal rye on September 26th last year. And you could count on one hand the number of germinated red clover seeds that were there at any point this past fall. And so very limited success. We think it may be attributed partially to some pesticide carryover that was applied during the growing season onto the corn and onto the soybeans, and then impacted the success of the red clover when we drone seeded it on. So this year we've paid special attention to what products were applied to which fields at what times to ensure that we don't have that as a limiting factor this year and see if we can get some success with the cereal rye. It's one that farmers are particularly interested in because of the nitrogen fixing capability of cereal rye and trying to get that nitrogen credit from that legume cover crop. And so we're going to try it again this year. We also used an earlier seeding date, and fingers crossed we have some more results to share with you as of next year. So moving right along here into the next research activity that we'll speak about today. This is the cover crop grazing activity led by Dr. Kimberly Schneider of the University of Guelph. And so what we're doing here is after the farmers harvest their wheat crop at 7 sites across Ontario, we plant an oat and pea cover crop that August. And then that fall, we split the field in half. We graze half of it with either sheep or beef cattle, and we leave the other half ungrazed. And we take samples of the soil and of the plants both before and after that grazing period that happens kind of later in the year, October, November, right now, actually, we have livestock out on the living lab plots as we speak. And so that's kind of the timing that we're looking at. So then come springtime, we take more soil samples in the spring, and then the farmer preps the land however they see fit to prepare it for corn planting. And then they plant the corn. We go out again, and when I say we, again, I mean the team of students and lab techs and Dr. Kimberly Schneider from the University of Guelph. So we go out and we sample that corn crop, like the stand count, some plant tissue samples from both sides of the fence, the grazed to compare it against the ungrazed. And then right now as well, we have our living lab plots from last year being harvested. The corn's being harvested right now. And we'll measure the yield from the side that was grazed a year ago and the side that was left ungrazed a year ago. And so this is how it's set up. Like I described, it's actually a 4-acre section that's depicted on the left side of the screen here. So 4-acre section fenced off. And it's got a physical electric fence down the middle, represented by this dashed line. And then this is for just for sampling purposes. These lines don't exist in the field. They're just marked by flags. But the researchers have split the 4 acres into 8 quantiles for sampling purposes. So they grab a composite sample from within each of these 8 quantiles, and that's how they get their results from the half that's grazed and the half that's ungrazed. And this is a photo from last year, and you can just see we're standing right here at the end of that electric fence looking down it. It's very obvious with the left side being left ungrazed and the right side having been grazed a few days before this photo was taken. And so we haven't finished a full cycle of this project yet because the grazing happened a year ago, but then the corn was planted this spring and that corn is actively being combined right now. So we're just a few weeks away from having the rest of this data to round out year 1 of this project. But for now, I'll just share some of the soil samples that we've collected so far that compare the grazed and ungrazed treatments. So on the left side of this graph, we have soil samples that were taken before the grazing period, and they're from both sides of the fence combined. And so there's organic matter, soil respiration, and potentially mineralizable nitrogen. Then down the center column and on the right side, these soil samples were taken after the grazing period. And in the center, it was from the grazed half of the plot. And on the right-hand side, it was from the ungrazed half of the plot. So looking at organic matter, it takes a while to drive any soil organic matter changes in the soil. And so we would not expect that any variation here was due to the grazed versus ungrazed, but rather just natural variation. And then with soil respiration, there's really no difference between the grazed and ungrazed, but there was a difference between the post-grazing sampling time and the pre-grazed sampling time. So that's just the difference here, likely due to just the timing of it. This was earlier in the season, warmer temperatures, moisture available, et cetera, maybe more soil respiration going on. And then on the right-hand side, later in the season, less soil respiration, whether it was grazed or ungrazed. So then at the bottom, we have the potentially mineralizable nitrogen. And the lowest score was here on the left column, the field average before any grazing occurred. And then the highest nitrogen score was from the post-grazing sampling event on the side of the fence that was grazed. And then, just less than that was the ungrazed side. And so that column specifically was one that we saw across several sites a similar trend, where with organic matter, for example, this was not a consistent trend with this is just a chance that the post-grazing grazed side of the fence had the highest organic matter. But down here with the nitrogen, that may have been something that was driven by the active grazing on that land. So things we're learning, like I said, all of these projects are either carbon sequestration or greenhouse gas mitigation. This one in particular, we're taking those soil samples, we're determining if we can sequester some carbon in the soil by grazing cover crops after harvesting wheat. We're also measuring the impacts that this practice may have on soil health and fertility. And then we're also asking the farmers, how is this working for your farm? Is it feasible? Is it practical? Is it advantageous for you to have a longer grazing season on your farm? And then that ties in nicely to, is it economically feasible, this longer grazing season on your farm? Is that saving you some money, some housing costs and some feed costs by grazing cover crops that were planted after wheat harvest? And then also on the economic front, of course, we're taking those yield measurements of the corn on either side to determine if there's either a yield advantage or a yield disadvantage from conducting this practice. And so stay tuned. We will have more information about these projects and these results as we progress through the second and third and fourth years of the project. Okay, wonderful. This is the final activity that we'll dive into today, led by several researchers from Agriculture and Agri-Food Canada, as well as a researcher from the University of Guelph. And our main objectives with the nitrogen activity are to reduce those greenhouse gas emissions, in this case, nitrous oxide emissions from nitrogen fertilizers. But then we're also looking to optimize nitrogen applications to improve profitability on the farms. And the way we've decided to do this is by using nitrogen inhibitors in grain corn production. So this is an example from 2024 at a site we had set up in Harrow, Ontario. The yellow strips are representing the control treatment that we applied to these fields. And so how do we determine what the control was? We simply asked the farmer, hey, if you didn't have a living lab trial on your farm right now, how would you treat that field in terms of nitrogen application? And so in this case, the farmer injects 180 pounds per acre of nitrogen and does not use an inhibitor. That's their standard practice. Then we apply three other treatments. So in the purple here, we use the same rate of nitrogen that they use in their control treatment, and we add an inhibitor to it. In the pinkish color here, we reduce the rate of nitrogen by 82 to 85%. Sorry, not by 85%, but to 85% from the 100% maximum. So like a 15% reduction in nitrogen. And we try that without an inhibitor and compare that to what's in the blue here at the bottom with the same reduced rate of nitrogen, and we add an inhibitor. So then what do these results look like? So again, these are the real results that we collected from that site in Harrow in the 2024 growing season. So on the left-hand side of this chart, we have the full rate of nitrogen, no inhibitor. That's the control. That's the standard practice. And we yielded about 236 or 7 bushels to the acre in that case. Then in treatment 2, we use the full rate of nitrogen. We add an inhibitor to it. And in this case, we see an 8.5 bushel to acre increase, a yield advantage. Now, this treatment would cost us a little bit more to plant and apply because we don't have any nitrogen savings and we add an inhibitor to it. And so it was a little more expensive to apply, but this 8.5 bushel to the acre increase was more than enough to compensate for the cost of the inhibitor. Now in treatment 3, we've reduced the rate by 15% in this case, and we don't add an inhibitor. And this appears to be a nitrogen limited trial because a treatment, sorry, because of course we have the reduced rate, no inhibitor, and we have a reduced yield, likely due to the lack of nitrogen in that treatment. And then in treatment 4, we use this same reduced rate of nitrogen, but we add an inhibitor, and we've actually now out yielded the control by 5 bushels to the acre. We didn't out yield treatment 2 that had the full rate of nitrogen with the inhibitor. However, we did have the highest profit in this case. What happened there? Well, we had nitrogen savings. We applied 15% less nitrogen on treatment 4 than we did treatment 2, and we applied the same inhibitor cost to each of these treatments. And so those nitrogen savings were actually enough to compensate for, a few less bushels in treatment 4 when compared to treatment 2. And so it's just something that's interesting. We're not always going for just the highest yield. We want to make sure that we're also looking at what's the most profitable. And I should mention, of course, these numbers are very sensitive to the assumptions you make. And so I used $5 per acre per bushel of, $5 per bushel of corn, and I used 80 cents per pound of nitrogen. So I think that's fair. If you disagree, you can rerun the numbers yourself with your own input costs and see how it adjusts. But the pattern stays the same with the increase of yield here, the decrease here, and then to get back up. Okay, I better keep moving here. So at another site, this one's near Hamilton, again last year, what we're looking at here, the x-axis is exactly the same, except we had a little bit more of a decrease in the nitrogen rate. But otherwise, full rate, no inhibitor, that's the control, 226 almost bushels to the acre. Then we take that full rate, we add an inhibitor to it, we didn't see any yield advantage. We yielded exactly the same in treatment 2 as we did treatment 1. So this is less profitable than the control by the exact cost of the inhibitor per acre, which in this case was just shy of $10. In treatment 3, we have the reduced rate of nitrogen, and then we have some nitrogen savings from that. However, this 7.3 bushels to the acre yield hit was too expensive of a loss to compensate for that nitrogen savings, and so less profitable again in this treatment 3. Then we move on, treatment 4, reduced rate. We have nitrogen savings. We add the cost of inhibitor though, and the cost of this 2.3 bushel to the acre yield drag, and we're still up at the most profitable treatment in this case because of those nitrogen savings, more than enough to compensate for the reduced yield in treatment 4, which is fairly small reduction. And one thing I'll mention before I move on, it looks to me like in this case, the control treatment was not nitrogen limited. If the control were nitrogen limited, it's likely that when we add the inhibitor in treatment 2, we prevent losses to the atmosphere and through leaching. We have more nitrogen available for the crop throughout the growing season. We would have seen a yield advantage had the control been nitrogen limited. And that's what we saw. This is back to the first example I showed. That's what we saw here. It looks like the control is nitrogen limited here because when we add nitrogen by losing less to the atmosphere, we have a yield advantage, and that we did not see in this case. So in this case, it made a lot of sense to reduce the rate and add the inhibitor. And we'll move right along. This is a chart that is estimating the greenhouse gas emission intensity per unit of grain for each of these 4 treatments from the site 34 that I just showed in the previous slide. And so this is made from a computer modeling system called Holos, and we input all of the data that we collect from the farm about operational data and fertilization practices. It takes into account soil type, yield, weather patterns throughout the growing season, a whole host of information, and then we tweak our inputs based off of which treatment was applied, and then it estimates the greenhouse gas intensity of each of those treatments. And so on the left-hand side, we have the control. It has the highest estimated amount of greenhouse gases per unit of grain that we produced. The next two treatments, we have the treatment two where we added the inhibitor but had the full rate of nitrogen. These two are switched from the slide above. Sorry, that's a little bit unclear. This is treatment three, where we have the reduced rate of nitrogen and no inhibitor added. And we have very comparable amount of greenhouse gas intensity in these two treatments, less than the control. And then in treatment four, where we combine those practices of reducing the rate of nitrogen and using an inhibitor, we have the fewest greenhouse gas emissions per unit of grain. And if you remember back, this was also the most profitable treatment of the four. So most profit, least impact in terms of greenhouse gas emissions. And so that's an exciting thing to see. And we saw that over and over again, where the most profitable treatment was one of these two, and that was also the treatment that had the fewest greenhouse gas emissions. Those things can go and do go hand in hand fairly often. Okay, another example here where we have the control in treatment two yielding basically the same. Treatment two cost us more to plant by exactly the amount that the inhibitor cost per acre. That's what that $9 is. They used a different inhibitor, cost different amount in this case, but not by much. All of these treatments are actually within 5 bushels, so don't let the zoomed in chart fool you. This is only 4.7 bushels per acre less than the control. And we have nitrogen savings in this case because of the reduced rate of nitrogen applied. So we are actually slightly more profitable in the control using the numbers I've used for that calculation. And then our most profitable treatment by a small margin is treatment four, again, where we reduce the rate of nitrogen and we added the inhibitor, and we've got a little bit of a yield advantage over there. But all four of these treatments really tight together. And again, greenhouse gas emission estimate. The scale is different on this one because this is greenhouse gas emissions predictions per hectare instead of per unit of grain. It's just another way of looking at it and can put it into context, two different charts of these predictions. So kind of what you might expect to see. You have the control with predicted to have the most greenhouse gas emissions per unit and or sorry, per hectare, and the fewest when we combine using less nitrogen and add an inhibitor. And so yes, that's again the most profitable treatment and the fewest greenhouse gas emissions, kind of a double win there. Okay, I've got two more to share with you. I am coming towards the end, so if you're snoozing behind your cameras there, then you come around to ask a question maybe at the end of the presentation in just a few slides. This is another site I wanted to share. It was done in Peterborough, and so here, what it looks like to me, like I mentioned before, the control appears to be nitrogen limited because when we added an inhibitor to the control rate and we kept more of that nitrogen available to the plant for more of the growing season, those plants made good use of it and put on almost another 9 bushels to the acre of yield. And when we reduced the amount of nitrogen from an already limited control rate, it didn't matter whether we added an inhibitor or not. We had a yield hit, and significant enough that this would cost the farmer serious amount of money per acre for these yield hits. And so we do see the trend that we like to see, like this increase in yield from treatment three to treatment four indicates that we kept more of the nitrogen in the soil throughout more of the season when we added an inhibitor to this 85% rate here to here. But it really wasn't enough considering the control was likely nitrogen limited itself. Didn't matter that we added the inhibitor or not. So this is a real testament to how important your nitrogen rate is in the first place. And I know that's the age-old question, how much nitrogen do I need to apply? Ask me in November, right? Because it's they say about a bushel per pound of nitrogen, a bushel of yield per pound of nitrogen. You don't know how much yield you're going to have until November. But if you were to experiment on your farm and you used your control rate of nitrogen, and then you think to yourself, using the correct theory that if I add an inhibitor, I'll keep more nitrogen in the soil available to the plants for more of the growing season. So I should be able to reduce my rate from my control and apply an inhibitor. So if you only had these two treatments in your field side by side, a control and a reduced rate plus inhibitor, and you saw this almost 7 bushel to the acre yield drag or whatever yield drag, if you did see something like that, you'd be fairly disappointed in the performance of your inhibitor and likely veer away from trying that type of thing again or trying to expand it on more acres. So it's just something to consider. Maybe the problem is that the control rate wasn't enough nitrogen for that year and was yield limited in itself, in which case you would want to add an inhibitor to your control rate without reducing your nitrogen rate at all, and you may have a big enough return to pay for that additional expense, like we've seen over and over in the examples today. And before I click to the next slide, which is a little bit of a scary sight, I want to be transparent. I want to show, a good representation of all of the results we collected. We had 14 sites throughout 2024 with a trial that followed a very similar, like x-axis, the 4 treatments last year. And out of the 14, 12 of them had one of the treatments, at least one of the treatments with an inhibitor as the most profitable treatment. 2 of them did not. And so we're conducting research out on real working farms. There's variables that we simply can't control for, like the weather and like natural variation within the soil, soil type and soil fertility, and maybe weed and disease and other pest pressures that we can't control for. And so sometimes we have results that I simply don't have a great explanation for you today, but I'll show you in a moment. Excuse me. I'll show you in the moment, just on my last slide, I promise, last slide coming up next, that what we're doing in 2025 to try and add a little bit of context so that when we see a result like the one I'm showing in front of you, we may be able to have a better explanation loaded up for you, if I was to be invited again to present next year. So same x-axis in this case, full rate, no inhibitor, highest yielding, highest profit. Full rate inhibitor, we lost 3 bushels to the acre. Let me draw your attention briefly to the y-axis where you see we're growing 275 bushel corn in this control. So this 3 bushel hit, did anyone else just get an emergency alert on all of their cellular devices? Sorry about that interruption. I heard on the radio this morning there would be a practice run of that system today, so I believe that's all it is. Anyway, so this 3 bushel to the acre hit in the full rate plus the inhibitor, that's actually not a significant difference because, we're looking at 275 bushel to the acre corn compared to 272. Then when we reduce the rate of nitrogen, it appears to be nitrogen limited here, certainly. But even in our lowest yielding treatment, which was treatment 4 in this case, we're still above 250 bushels to the acre. What's really puzzling about this trial is why wouldn't treatment 4 be slightly higher than treatment 3 if the reason these 2 treatments are lower than the first 2 treatments is because they're nitrogen limited? I don't have an answer to that question loaded up for you today, but what I do have is a plan that uh, we did in 2025, so that if we have results like that again, we may have some extra context for you this year. So what you're looking at is a field that we had a nitrogen trial in this year. In this 4 acre section that I have highlighted, there are 12 treatment strips side by side by side by side. I just didn't label them in there because it gets too tight and convoluted. And then on the left side of the screen, this is the raw image taken by the drone. If you were to actually zoom in on that image, you could make out not just the individual rows of corn and count each row, you can also make out individual corn plants. That's how high resolution that drone imagery is. On the right-hand side is another one of those fancy NDVI images layers. So that's on top of the raw image. And again, anything that shows up green here is a dark green, healthy, photosynthesizing plant. And in this case, we expect all of that to be corn. And what shows up as red is either bare soil or corn that's yellowy and unhealthy and not photosynthesizing, has a lower concentration of chlorophyll in it. That's going to show up as yellow and as red. So if I bring it back to the raw image, this farmer decided to try 6 rows of zero nitrogen as just a little test plot right beside our living lab plot. So if you look where my laser pointer is right across the center, that's that zero nitrogen plot. You can see it in this image. And then if you come over here, you can see it again right here. That zero nitrogen plot goes the full length of the field. But this is what I'm talking about for adding context to results. What we see here, I've actually been out to this field twice myself to do some sampling for this project. And I can tell you from being there twice, what we see right across the front of the field here is a sandy knoll. And what we see right here is another sandy knoll. It runs on a bit of an angle back up towards the front, towards the first one. And even back here, this is a sandy knoll that tails into the living lab part of this plot up here with a little bit more of that yellow rather than green. And so 2025 was notoriously dry all over the province, as far as I understand it, at least. And this farm specifically warned me that they had a severe drought this year. Those sandy knolls, they always struggle for moisture on, but this year in particular, that corn looked tough. So you can see that show up in the NDVI. And what my point is that this sandy knoll, this natural variation that has nothing to do with the plots that we've applied to this area, is not equally distributed throughout the plots. It runs on a bit of an angle like so. And you can see even at the other end of this plot, the entire south half of this plot has more of those red and yellow areas that were caused due to drought stress, whoops, and had nothing to do with the treatments applied. And then north half of this plot, yes, there is some of that sandy knoll ripping through them up here at this end of the field, but they just have a lot more area that were in lower part of the field where there was a little more water holding capacity, and that corn survived a little better throughout the drought and will undoubtedly yield higher. So regardless of what treatments were applied, this south half of this plot will not yield as well as the north half of this plot. And so something like this may have happened in the results I showed above, but we don't have NDVI images from last year. It's something new that we added for 2025 to add some context so that we can explain when we have unexpected results. And it's an interesting layer to look at for us. It's an interesting layer for the farmer to look at. For this farm in particular, it was no surprise. He knew he was nitrogen limited in those areas, and you could tell from the roadside that that was the case. But um, that's just something I wanted to share with you, something we're excited about that we've done for 2025, and an example of how these living lab trials as a whole, we're always learning from the year before and adapting our practices and our research so that we can improve each year and keep our results keep our results applicable to real working farms in Ontario. And so that's what we're all about. This is a slide of our Living Lab partners. We're very grateful for the top row there, our core partners who have contributed funding to the project, and then below that, a handful of our research partners for various projects. I think that's everything I wanted to say. I do apologize. It looks like I've gone a little bit longer than I had anticipated, but if anyone has any questions, I'd be happy to take them. Maybe there's already some in the chat. I apologize. I wasn't actually paying attention to that throughout the presentation. But also, if you've attended today in need of a KSE, a knowledge sharing event for, I believe we've approved for nitrogen management and cover cropping categories of that, you can scan the QR code and fill out the form that links you to. So thank you very much, everyone.
Thanks, Owen. Yeah, if anyone has any questions, please leave them in the Q&A spot. But if you have to run, thank you all so much for joining us today. You'll receive a recording of this webinar, and hopefully we'll see you at the next winter webinars. But Owen, we have a few questions already.
Great.
We have, is there a cost comparison available of drone application versus drill versus broadcast?
Excellent question. Excellent. Yes. And yes, we do have that information. We're collecting it. We do an economic analysis on each of these strips. It was a little tricky because when we hired the drone to come out and seed our plots, they did several plots all over the countryside all in one day. And so it's a little bit challenging. But we did ask, what would generally your cost be? And he says for a 10 pounds to the acre application. So if you were applying, let's say red clover, for example, is very small seed, you generally would have that lower seeding rate of just 10 pounds to the acre. He can seed it for as cheap as $10 or $12 to the acre, depending on, the size of your field and the size of the project. Then as you go up to the 50 or 60 or 80 pounds to the acre of seed being applied, that's when the cost of the drone application shoots up. So up to $22.50 per acre. And it depends on who you have doing the work for you, presuming that you're having it hired done. But yeah, $22.50 or up to $30 an acre for those 80-pound to the acre applications. Again, depending on who you have hired for it and how big the job is in total. And as for the drilled and the broadcast spinner spread, I mean, you likely have an idea of what it costs you to drive your own seed box through the field. But if you were to hire it done, that can range from $25 to $35 an acre, I'd say. And yeah, thanks for that question. Really good question.
Our other question is the idea that OSCIA will promote these BMPs based on the results of these trials, or are they too location specific and only help the individual farmer?
Wow, another great question. So yeah, no, the intention is absolutely to share these results with the wider farm community. And what we've done, if you remember way back an hour ago at the beginning of my presentation, there was a map that had a dot that represented each of our sites. So we are spread across the province. Nitrogen trials, for example, that is the largest project. We have 14 of them. They range from the farthest southwest you can go, like Harrow, Ontario, up to Ottawa, up to Stayner, and everywhere in between along the west coast, in the Hamilton area, around Guelph. So we hope, and we're also collecting background data from each of these sites. So that's what I mean by that: soil type, heat units, crop variety, like their yield goals, their management practices, whether it's no-till or cover cropped or planted green or strip-tilled. And we also have soil tests that show their fertility, their base fertility already. So we're hoping we'll have enough context by the time we replicate in this case, the nitrogen case, these 14 sites across three or potentially a fourth growing season will have enough data from enough areas across the province and enough contexts, like enough soil types and fertility levels, for example, and management systems, that we can have data that's applicable to all types of farmers across all of Ontario. That's our goal, certainly.
Amazing. All right. Well, I don't see any more questions. So I will wrap up our webinar here.
I will stop sharing. Huh.
I think I've already stopped sharing for you.
Oh, okay. Thank you.
Already on it. Okay, great. So thank you again, everyone, for joining us, for participating, and thank you, Owen, for sharing your expertise. Once again, thank you to the Greenbelt Foundation for supporting this webinar. If you enjoyed this webinar, please considering donating to OFT using the link in the chat so that we can continue offering these webinars and other accessible resources. I'll also invite you to take a moment to fill out our webinar feedback form to help the ongoing improvement of our webinar offerings. Your responses will be anonymous. Lastly, if you would like to get more involved with OFT or learn more about us, you can explore our farmland protection resources by visiting our website at ontariofarmlandtrust.ca. You can also remain up to date with our work by following us on social media, as well as subscribing to our newsletter. And you can become a donor, a member, or a volunteer your time to help accelerate our farmland protection initiatives. And finally, our events don't end here. We have two more winter webinars coming up in January and December. So you can scan that QR code on your screen to learn more about those and register for those. And then we have our annual Farmland Forum happening next March on March 19th in Elora. This will be an in-person event, and announcements on our theme and registration are to come. So if you'd like to learn more about the forum, you can visit the link in the chat. And so with that, that is everything. Thank you all once again for joining us today. You'll receive a link to the recording shortly. Thank you, Owen. Thank you, Rachel, for helping out. With that, I hope you all have a lovely rest of your day.